In 1876, engineers working for the Central Pacific Railroad presented their calculations to company executives. They had designed a wooden bridge to span a canyon in the Sierra Nevada mountains. The bridge would stand 220 feet above the canyon floor. It would stretch over 1,100 feet from rim to rim, and according to their mathematics, when winds exceeded 40 miles per hour, the entire structure would sway approximately 3 feet in either direction. The executives approved construction anyway. Trains crossing that bridge would be limited to 5 miles per hour. Walking speed, slower than a man could jog, because at any faster pace, the harmonic vibration of the locomotive combined with the natural flex of the timber could amplify until the whole structure tore itself apart. This was not a failure of engineering. This was the engineering working exactly as designed. For nearly 4 decades, wooden railroad trestles like this one were the only way to push railroads across the American West. Stone was too heavy to transport. Steel was too expensive to manufacture in the quantities needed. But timber grew in the very mountains the railroads needed to cross. And so American engineers did something that still defies belief when you stand beneath one of these structures today. They built massive wooden bridges across canyons so deep that a man falling from the top would have time to scream, pray, and make peace with his death before he ever hit the ground. This is the story of those bridges, the men who designed them, the workers who built them with their bare hands, and the passengers and crew who trusted their lives to structures that groaned, swayed, and sometimes collapsed without warning. The problem that wooden trestles solved was fundamentally geometric. When you look at a map of the American West, you see mountain ranges running north to south. But railroads needed to run east to west. That meant crossing terrain that had stopped human transportation for thousands of years. The Sierra Nevada mountains don't gradually rise from the California valleys. They erupt. You can be standing in relatively flat farmland, and within 20 miles, you're looking at granite walls that rise 8,000 feet into the sky. Between those walls are canyons carved by rivers over millions of years. Canyons so deep and so steep that building a road down one side and up the other would require grades no locomotive could climb. European engineers had solved canyon crossing problems for centuries using stone arch bridges. The Romans built aqueducts that still stand today, but stone arch bridges require something the American West didn't have: time. A proper stone arch takes years to construct it. You need skilled masons who understand how to cut and fit each block. You need scaffolding that can support thousands of tons of stone until the keystone locks everything in place. And you need a foundation solid enough to handle the massive compressive forces of the arch. The railroad companies didn't have years. They had months. The federal government had promised land grants based on miles of track completed. Every day of delay cost money. Every month without progress meant competitors might reach valuable territory first. The race across America was exactly that, a race. And stopping to build stone bridges across every canyon would mean losing. Steel offered another theoretical solution. By the 1860s, engineers understood that steel trusses could span distances that would make stone masons weep with envy. But American steel production couldn't come close to meeting railroad demand. The Bessemer process was still new. Steel mills existed mainly in the East. Transporting finished steel girders across the continent to build bridges in the mountains was logistically absurd. You'd need the railroad to already exist to ship the materials needed to build the railroad. That left timber. The timber solution wasn't a compromise. That's the crucial thing to understand. In the hands of the engineers who perfected it, timber bridge construction became an art form that pushed the material to its absolute physical limits. These weren't rough frontier structures thrown up by amateurs. They were precisely calculated machines made of wood. Every beam, every joint, every iron bolt was placed according to mathematical formulas that predicted exactly how much weight the structure could bear before failure. The fundamental unit of wooden trestle construction was called a bent. Picture a capital letter A without the crossbar. 2 massive timber posts, typically 12 inches square, driven deep into the ground or anchored to bedrock, rising vertically and leaning slightly inward toward each other. At the top, a heavy horizontal beam called a cap connected the 2 posts. Below that, cross-bracing ran diagonally between the posts to prevent the whole structure from racking sideways in the wind. A simple bent might stand 30 feet tall, but canyons weren't 30 feet deep. They were 200 feet deep, 300 feet deep. Some approached 400 feet. Building a single bent that tall wasn't structurally possible. The posts would buckle under their own weight long before a train ever crossed, so engineers stacked bents on top of each other. They called this tower construction. The first bent was built on the canyon floor. Its cap beam became the foundation for the next bent above it. That bent's cap became the foundation for the next. And so on, rising story by story until the structure reached rail height at the canyon rim. The tallest wooden railroad trestle ever constructed in the United States was the Lyman Viaduct in Connecticut. It stood 137 feet tall, but Western trestles routinely approach 200 feet. The Cascade Division trestle near Stampede Pass in Washington. Territory reached 190 feet. The timber structure at Secret Town in California climbed to over 200 feet above the valley floor. And the width of these structures, spanning sometimes a quarter mile or more, meant that dozens of towers had to be constructed, each one perfectly aligned with its neighbors, connected by horizontal stringers that carried the actual track. Now, put yourself on that construction site. You're a laborer in 1877. You've signed on with a railroad construction crew because the pay is better than farming, and you heard there was work out west. You show up at a canyon rim in Northern California. You look down. The bottom is so far away that the river below looks like a silver thread, and your foreman tells you that you're going to spend the next 6 months building a wooden bridge across this gap. The first challenge was getting to the bottom. Construction started at the canyon floor, not the rim. Workers had to descend with their tools, their supplies, and eventually the massive timbers that would form the bridge structure. Some canyons had existing trails. Most did not. Work crews spent weeks building switchback paths down canyon walls, blasting ledges with black powder, carving footholds into stone with hand tools. Men fell during this preparatory work. Their names rarely made it into official records. Once workers reached the canyon floor, they began the foundation work. Tower footings had to rest on bedrock or driven piles. In river canyons, this meant diverting water flow, building temporary cofferdams, working knee-deep in freezing mountain runoff while trying to set timbers plumb and true. The temperature of Sierra Nevada snowmelt rarely exceeds 40 degrees. Workers stood in that water for hours at a time, their legs going numb, their hands so cold they could barely grip their tools. The men who did this work were often immigrants. Chinese workers made up a significant portion of Central Pacific crews, sometimes as much as 90% of the labor force. And Irish workers dominated Union Pacific gangs. They brought skills learned in their home countries, adapted to conditions that would have seemed impossible back in Cork or Canton. These weren't unskilled laborers. They were experienced construction workers who understood timber, understood rope work, understood the physics of lifting heavy loads with simple machines. The railroad companies knew this. They recruited specifically from populations with construction experience. The timber itself came from nearby forests. Douglas fir was preferred for its combination of strength and workability. A Douglas fir beam could bear more weight per square inch than almost any other American softwood. Redwood, where available, resisted rot better than almost any other species. Its natural tannins repelled the fungi and insects that could hollow out a Douglas fir post in a decade. Pine served when nothing else was at hand, though engineers knew pine was weaker and required more frequent inspection. Logging crews worked ahead of construction teams, felling trees and rough milling them into the massive beams needed for trestle work. A single tower might require 30 or 40 large timbers. A complete trestle across a major canyon needed thousands. The logging operation was itself a significant undertaking, employing hundreds of men with axes and crosscut saws, dragging felled trees to temporary sawmills with teams of oxen or mules. Transporting these timbers to the construction site required its own engineering. On some projects, workers built temporary wooden flumes. Water diverted from mountain streams carried logs down to the canyon and controlled descents. The logs floated in channels just wide enough to contain them, racing downhill at speeds that could exceed 30 miles per hour. Men stationed along these flumes used pike poles to keep logs from jamming, a job so dangerous that drowning was a common cause of death, even for workers who never went near the actual bridge site. On other projects, they used gravity chutes. Greased wooden troughs sent timbers rocketing downslope at terrifying speeds. A 12-inch square beam 40 feet long weighs nearly 3,000 pounds. When that mass starts moving down a mountain, physics takes over. Men stationed along these chutes used cant hooks and raw courage to keep logs from jamming or careening off course. A log moving at 40 miles per hour doesn't care what's in its way. Workers who got caught by runaway timber were crushed without ceremony. Raising the timbers into position was perhaps the most dangerous phase. The first few bents could be assembled on the ground and tilted upright using rope tackles and human muscle. A crew of 20 men hauling on hemp rope could generate thousands of pounds of lifting force, enough to raise a completed bent frame from horizontal to vertical in a matter of minutes. But once towers rose above 50 or 60 feet, ground-based lifting became impractical. Workers had to climb the partially completed structure with ropes and pulleys, rigging temporary derricks at each level to hoist materials higher. Picture this. You're standing on a platform of rough-sawn planks nailed to the cap beam of a bent 120 feet above the canyon floor. The platform is maybe 3 feet wide. There's no railing. The wind coming up the canyon makes the whole structure vibrate beneath your feet. You can feel each gust through your boot soles, a tremor that runs up your legs and settles in your gut. And your job is to catch the end of a 16-foot timber being swung toward you on a rope, guide it into position, and hold it steady while another worker drives iron drift pins through pre-drilled holes to lock it in place. The drift pins were critical. Unlike nails, which depend on friction to hold, drift pins were iron rods driven completely through overlapping timbers. They were typically 3/4 of an inch in diameter and up to 2 feet long. A worker would drill a hole slightly smaller than the pin's diameter, then drive the pin through with a sledgehammer. The iron deformed slightly as it passed through the wood, creating a mechanical bond that wouldn't pull apart under load. Each pin required dozens of hammer blows to seat fully. The sound of that hammering echoed off canyon walls, a rhythmic pounding that marked the progress of construction. This sounds simple until you realize that workers were swinging 16-pound sledgehammers while balanced on platforms barely wider than a dinner plate, 100 feet or more above certain depth. The sledgehammer swing itself requires full body rotation. You plant your feet, twist at the waist, bring the hammer up and around, and slam it down on the pinhead. Do that while standing on solid ground, and it's merely tiring. Do it on a platform that bounces with each impact, surrounded by nothing but air on 3 sides, and it becomes an exercise in controlled terror. Falls happen constantly. The official records of railroad construction casualties are notoriously incomplete. But historians estimate that building the Transcontinental Railroad cost between 1 and 3 workers' lives for every mile completed. Many of those deaths happened on trestle construction. A man named Wong Fook fell from the Bloomer Cut trestle in 1866. James McCarthy slipped from scaffolding near Colfax the same year. Their deaths were noted in foreman's logs and forgotten within weeks. The work continued. Once the main structure reached rail height, workers installed the stringers. These were the heavy horizontal beams that actually carried the track. Stringers ran from tower cap to tower cap, typically spanning 20 to 30 feet between supports. They had to be perfectly aligned so that the rails mounted above them would be level and straight. Any deviation would cause wheels to climb, derailments to occur, or in the worst case, the uneven loading to progressively destroy the structure beneath. The rails themselves came last. By this point, the railroad company was often screaming for the construction crew to finish. Every day without completed track was money lost. Workers laid rails across the stringers and spiked them down while the wood beneath them was still settling, still adjusting to its loads, still green in some cases because there hadn't been time to properly season the timber. And this brings us to the engineering calculations that made wooden trestles both miraculous and terrifying. Wood is not like steel or stone. It has a grain, it flexes, it absorbs moisture and swells, dries out and shrinks. Two pieces of timber cut from the same tree might have dramatically different strengths depending on which part of the trunk they came from. Heartwood from the center of a mature tree is denser and stronger than sapwood from the outer rings. A knot where a branch once grew creates a weak point that can fail without warning. An engineer's designing wooden trestles had to account for all of this variability while calculating structures that would carry hundreds of tons of locomotive and freight. The key insight that made large wooden trestles possible was the concept of elastic deflection. When you put weight on a wooden beam, it bends. If you remove the weight quickly enough, the beam springs back to its original shape. This is the wood's elastic range. But if you exceed a certain load, or if you apply the load for too long, the wood undergoes plastic deformation. It bends and stays bent. Continue loading and the fibers separate. The beam fails. Engineers calculated exactly how much deflection was acceptable in each component. Stringers carrying the actual track load might be allowed to flex 2 inches under a passing locomotive. Tower posts might be allowed to compress a fraction of an inch under static load. The entire structure, taken as a whole, might sway several feet in high wind without exceeding the elastic limit of any individual component. These calculations filled notebooks. They required understanding of material science that was still being developed. The engineers who did this work were inventing their discipline as they practiced it. The problem was that these calculations assumed ideal conditions. Perfectly seasoned timber with consistent grain, joints that remained tight over time, iron hardware that didn't rust and weaken, a weather that stayed within predicted parameters. In reality, conditions were never ideal. Wet timber was weaker than dry timber. A beam that could safely bear 20 tons when dry might fail at 15 tons when saturated. The massive posts at the base of towers, constantly exposed to rain, fog, and in some cases standing water, gradually absorbed moisture and lost strength. Nobody could see this happening. The wood looked the same from the outside. Only testing could reveal the degradation, and testing meant either destructive sampling or sophisticated instruments that didn't yet exist. Dry rot attacked wood from the inside, hollowing out apparently solid timbers until they were shells ready to collapse. Dry rot is caused by fungi that digest the cellulose in wood. The process is slow, taking years to progress from initial infection to structural failure. But it's also invisible. A post that looks perfectly sound can be 80% destroyed internally. The only way to detect advanced dry rot is to tap the timber and listen for the hollow sound that indicates the interior has been consumed. The joints were another failure point. Wood shrinks as it seasons. Tight joints cut from green timber became loose joints a year later as the wood dried and contracted. Drift pins that had been driven solid worked loose in their holes. Bolts that had been torqued tight found themselves spinning freely. The structure settled, shifted, and found new equilibrium states that the original designers never predicted. Without constant inspection and maintenance, a trestle could go from safe to dangerous in a single season. Wind loading was perhaps the most frightening variable. Engineers could calculate static loads precisely. They knew how much a locomotive weighed, how that weight was distributed across the wheels, how the stringers would deflect under that load. But wind was dynamic. It gusted and swirled. Meech Canyon winds, in particular, could be brutally unpredictable, channeling through narrow gaps and striking bridge structures from angles that the original engineers never considered. The 3-foot sway calculated for that Sierra Nevada bridge wasn't a failure. It was the structure doing exactly what it was designed to do. Flexible structures survive dynamic loads better than rigid ones. A trestle that swayed was absorbing wind energy that would have snapped a rigid structure apart. The wood fibers stretched slightly, the joints moved slightly, and the energy dissipated instead of accumulating. But that flexibility came with constraints. Trains had to cross slowly enough that their own vibration didn't add to the wind-induced motion. If a locomotive hit resonance with the bridge's natural frequency, the oscillation would amplify until something broke. This is why train speed restrictions on trestles were so important and so carefully calculated. When every wooden trestle had a rated maximum speed, typically between 5 and 15 miles per hour, Exceeding that speed was grounds for immediate dismissal. Engineers who pushed the throttle too hard on a trestle weren't just risking their own lives. They were risking the lives of everyone on the train and potentially destroying infrastructure that had cost hundreds of thousands of dollars to build. But train schedules were demanding. Passengers complained about delays. And freight shippers threatened to take their business elsewhere. And locomotive engineers, paid by the run rather than the hour, had financial incentive to make time wherever they could. The result was a constant tension between safety and speed, played out every day on every wooden trestle in America. And still, some bridges failed. The collapse of the Tay Bridge in Scotland in 1879 shocked the engineering world. 75 people died when a cast iron and wrought iron bridge gave way in high winds. The disaster prompted investigation into wind load calculations that had been considered adequate for decades. American wooden trestle designers paid attention, but wooden structures had their own failure modes that metal bridges didn't share. Fire was the most feared. A wooden trestle was essentially a massive pile of fuel waiting for a spark. Locomotive smokestacks threw cinders. Hot ash from fireboxes fell onto creosote-soaked ties. Sparks flew from brake shoes grinding against iron wheels. A single ember landing on dry timber on a windy day could turn a $250,000 bridge into charcoal in less than an hour. Railroad companies stationed water barrels and pumping equipment at major trestles. They built small sheds on the canyon rims housing hand-operated fire engines and coils of canvas hose. So some employed dedicated fire watchmen who did nothing but patrol bridge structures looking for smoke. These watchmen walked the trestle day and night, carrying buckets and wet burlap sacks to smother any burning sparks before they could spread. But fires still happened, and when they did, the results were catastrophic. The destruction of the original Boca and Loyalton Railroad trestle in 1899 demonstrated how quickly fire could consume a wooden structure. A spark from a passing locomotive ignited creosote on a summer afternoon. Workers noticed smoke within minutes, but by the time firefighting equipment could be mobilized, the fire had spread beyond control. The dry mountain air fed the flames. The creosote-saturated timber burned like it had been designed to burn. The entire trestle, nearly 1,000 feet long, was fully engulfed within 45 minutes. It burned through the night. By morning, only charred stumps remained where massive towers had stood the day before. Train wrecks on trestles produced some of the most horrifying accidents in railroad history. A derailment on solid ground might kill the crew, but leave passengers shaken but alive. A derailment on a trestle meant falling. Locomotives weighing 100 tons plunged into canyons, taking cars full of passengers with them. The fall could last several seconds from the highest structures, long enough for passengers to understand what was happening, long enough for people to scream. Bodies were sometimes never recovered from remote canyon bottoms. Wreckage sat for years, too expensive and too dangerous to salvage. The Boston Bridge disaster of 1891 killed nearly 30 people when a passenger train derailed on a trestle near Statesville, North Carolina. The locomotive left the rails just as it entered the bridge structure. The forward momentum carried the engine onto the span, but the twisting motion as wheels jumped, the tracks put lateral forces on the structure that it was never designed to withstand. Wooden towers that could support hundreds of tons of vertical load shattered under the sideways impact. The locomotive plunged off the side, dragging 4 passenger cars with it. Witnesses on the ground described screaming that echoed off the valley walls. The sound continued for minutes as trapped passengers cried for help in the wreckage. Rescue workers faced impossible conditions. The trestle structure was too badly damaged to walk on safely. Debris and bodies lay scattered across the canyon floor. Workers had to descend using ropes, picking their way through splintered timber and twisted iron in darkness lit only by kerosene lanterns. They found survivors pinned beneath overturned cars. They found bodies that had been thrown clear and lay broken on the rocks. They found passengers who had survived the fall only to drown in a stream 6 inches deep because they couldn't move with their injuries. The investigation afterward revealed that the derailment was caused by a rail that had shifted slightly out of alignment. perhaps a quarter inch. On solid ground, that misalignment would have caused rough riding and eventually been caught by a track inspector. On the trestle approach, it was enough to lift a wheel at precisely the wrong moment. The train had been traveling at the rated speed. The equipment was in acceptable condition. Everything had been done according to the rules, and 30 people were still dead. But here's what's remarkable. Despite the fires, despite the collapses, despite the deaths, wooden trestles worked. They carried millions of tons of freight and millions of passengers across terrain that had blocked human movement for millennia. They did this year after year, decade after decade. She's with maintenance schedules and speed restrictions that most of the time kept disasters at bay. The spectacular failures make the history books. The thousands of successful crossings that happen every day are forgotten. The men who inspected these bridges deserve their own recognition. Bridge inspectors, often called bridge walkers, had one of the strangest jobs in American industrial history. Their duty was simple: walk every wooden trestle on their section of track at least once per day. Tap every timber they could reach with a hammer. Listen for the hollow sound that indicated internal rot. Look for cracks, splits, insect damage, loose joints, shifting foundations, and report any problems immediately so repairs could be made before the next train crossed. Think about that job. Every day, you walk across structures 100 feet or more above the ground. You walk on narrow catwalks hung off the side of the trestle, or you walk on the ties themselves, on stepping carefully from beam to beam with canyon wind trying to push you off balance. In winter, you do this in snow and ice. Your hammer frozen to your belt, your fingers so numb you can barely grip the handrail. In summer, you do this in scorching heat that makes the creosote ooze from the wood and the entire structure smell like a tar pit. The inspectors develop their skills through apprenticeship and experience. A veteran bridge walker could tap a timber and tell you not only whether it was sound, but approximately how much life it had left. The pitch of the hammer sound indicated density. The way vibrations traveled through the wood revealed internal structure. They checked joints for gaps, counting how many threads of a bolt remained engaged, estimating how many more seasons before replacement would be necessary. Some bridge walkers became legendary in their divisions. I'm James Callahan, worked the Southern Pacific's Mountain Division for 37 years, personally inspecting the same trestles thousands of times. He claimed he could tell the condition of a bridge by the way it felt under his feet, that damaged structures had a different bounce, a different sway. Management thought this was superstition until Callahan identified a failing tower 3 days before it would have collapsed under a scheduled freight train. His hammer taps had found nothing wrong. But his feet knew. The inspectors caught problems that saved countless lives. A soft spot in a stringer here, a cracked post there. Drift pins working loose on tower number 7. Each report triggered repair crews who swarmed the structure, jacking up sections, sistering new timber alongside weakened beams, driving fresh hardware into joints that had loosened. The bridges were never static. They were living machines that required constant attention to remain safe. Repair crews worked in conditions as dangerous as original construction. They often had to work between trains, completing repairs in the few hours when traffic permitted access to the structure. Night work was common. Workers carried their tools and materials out onto trestles lit only by carbide lanterns, making repairs by feel as much as sight. Some railroads refused to close lines for maintenance, requiring repair crews to work while regular traffic continued. You'd be driving a drift pin into a joint when you'd feel the vibration of an approaching train. You had perhaps 90 seconds to gather your tools and move to a safety bay, a small platform built into the trestle specifically for this purpose, where you could flatten yourself against the timbers while 100 tons of locomotive thundered past inches from your body. As steel production expanded in the 1880s and 1890s, our railroads began replacing their most critical wooden trestles with permanent metal structures. The process was neither quick nor complete. A major trestle replacement might take years of planning and construction, all while the original wooden structure continued to carry traffic. Engineers designed steel trestles to be built around and underneath existing wooden ones, so that trains never had to stop running. The new structure rose inside the old like a skeleton forming within a chrysalis. Like some of the replacement projects were themselves engineering marvels. Workers assembled steel towers on the canyon floor, then jacked them upward section by section until they reached rail height. Hydraulic jacks, some capable of lifting hundreds of tons, raised entire steel bents in coordinated sequences. Only when the steel structure was complete and load-tested were the original wooden structures dismantled piece by piece from the top down. It was reverse construction, on taking apart by hand what had been built by hand decades before. Workers found their own footprints sometimes, marks left in preserved timber from the original construction years earlier. But not all wooden trestles were replaced. Remote branch lines, logging railroads, and short lines that couldn't afford steel construction kept their wooden structures in service well into the 20th century. Some are still in use today. The Georgetown Loop Railroad in Colorado still carries tourists across original wooden trestle sections. The Kinzua Bridge in Pennsylvania, before its partial collapse in 2003, was the longest wooden railroad structure in the United States, standing over 300 feet tall. When a tornado struck that structure and toppled most of the towers, the timber that fell had been in service for over 100 years. It hit the ground still solid, still sound, like still capable of bearing loads that would crush modern construction lumber. Standing beneath one of these surviving structures is an experience that photographs cannot capture. You crane your neck back and look up at post after post, bent, stacked upon bent, rising into the sky like some impossible wooden skyscraper. You see the individual axe marks where workers shape joints by hand. You see the dark stains where iron bolts have bled rust into the wood for over a century. You see the way the whole structure leans slightly, not from failure, but from 100 years of accommodation to load and weather and the imperceptible movement of the earth itself. Put your hand on one of those massive posts. The wood is cold, even in summer, dense as stone, harder than you expect. This single timber was a living tree when Lincoln was president. It was felled, milled, dragged up a mountain, and fitted into this structure by men whose names you will never know. They're all dead now, those workers, dead before most of our grandparents were born. But the thing they built with their hands and their sweat and their lives is still here, still standing, still doing the job it was designed to do. The last great era of wooden trestle construction ended around 1910. By then, steel was cheap enough and available enough that new construction almost always used metal. But the wooden bridges that remained represented something unique in American engineering history. They were the solution to an impossible problem, figured out by men who had no precedent to follow, no computer simulations to run, no safety factors calculated by generations of experience. They did the math with pencil and paper. They tested their theories by building structures and watching what happened. And when something failed, they studied the failure, adjusted their calculations, and tried again. The debt we owe these bridges is difficult to calculate. Without them, the Transcontinental Railroad would have taken decades longer to complete. The economic development of the American West would have been delayed by a generation or more. Cities that exist today might never have been founded. Industries that powered American growth into the 20th century might never have found the transportation links they needed to thrive. The timber trestles were more than infrastructure. They were the physical embodiment of American ambition, the willingness to attempt the impossible, and the stubborn refusal to accept that mountains could stop human progress. But the debt we owe the men who built these bridges is incalculable. They climbed where no rational person would climb. They balanced where a single slip meant death. They swung sledgehammers on platforms the size of card tables, 200 feet above solid ground. In wind and rain and snow and blazing sun, they did this for wages that wouldn't cover a modern worker's daily coffee habit. They did it because the work needed doing, and they were the ones willing to do it. The next time you cross a bridge, any bridge, consider this. Someone built it. Someone stood where the structure now stands, when there was nothing but empty air, and began the work of making nothing into something, on wooden railroad trestles, That work happened 100 feet above the canyon floor, on scaffolding made of the same timber that would become the bridge itself. The workers were their own safety net. If the scaffolding held, they'd live to finish the job. If it didn't, they'd fall. Most of them never saw their names in any history book. Most of them never received any recognition beyond their weekly pay envelope. They were laborers, immigrants, drifters, men running from something or toward something. Men who needed work and didn't mind that the work might kill them. We drive across bridges today without thinking about the engineering that holds us up. We certainly don't think about the workers who built that engineering into reality. But for 4 decades, the American West was connected by structures that required men to look straight down into canyons that would swallow cities, and then to build anyway. To walk out onto platforms narrower than a sidewalk, 100 feet above certain death, and drive iron through wood with a sledgehammer. That took something more than skill. It took something more than courage. It took a kind of trust in mathematics and materials that most of us will never be asked to demonstrate. The engineers trusted their calculations. The workers trusted the engineers. The passengers trusted the workers. And somehow, most of the time, that chain of trust held. The wooden trestles that still stand are monuments to that trust. They're also monuments to their own obsolescence. Steel replaced them because steel was better in almost every way. It was safer, more durable, and less prone to fire and rot, and the 1,000 small failures that required constant vigilance to detect and repair. The wooden bridges did their job, and then they stepped aside for their successors, leaving behind only a few surviving examples to remind us what was once necessary and what was once possible. If you ever get the chance to see one of these structures in person, take it. Stand beneath it, look up, feel the weight of it pressing down toward you. Think about the men who stood where you're standing, but with nothing above them except sky, and who then built what you're now looking at. They deserve to be remembered, not just as statistics in some historian's calculation of railroad casualties, not just as anonymous labor that made someone else rich. They deserve to be remembered as men who did one of the most dangerous jobs in American history, who died doing it in numbers we'll never accurately know, and who left behind structures that still stand as proof that human beings can build almost anything if they're willing to pay the price. The wooden railroad trestles of the American West were that price made visible. Every beam was bought with risk. Every bolt was driven by hands that knew what would happen if they slipped. On every crossing was an act of faith in mathematics, in craftsmanship, in the accumulated knowledge of engineers and builders who had figured out, through trial and error, and sometimes tragedy, how to make wood bear loads that wood was never meant to bear. Those bridges swayed in the wind. They creaked and groaned under passing trains. They required constant attention to remain safe. And for 40 years, they were the only thing standing between the American dream of a continental nation and the geographical reality of mountains that seemed designed to keep that dream from ever coming true. The men who built them deserve a monument. The bridges themselves are that monument. And now you know the story behind them. If you want to see another piece of forgotten American industrial history, the video on screen right now covers the men who built the tunnels beneath these same mountains, blasting through solid granite with nothing but black powder and human muscle. Subscribe so you don't miss it.